Good evening, everybody. We're going to have one little short podcast here on ionization energy. Hopefully it's a concept that you'll understand very quickly now that you are experts in atomic size. All right, ionization energy is the first ionization energy means that it just means the first electron that's going to be removed. And it is the energy required to remove an electron from an atom in the gaseous phase. Okay, so if we think about this, we have element X, whichever element it is that you are thinking about, and we have all this energy coming into the system. We've talked a lot about this, where this energy is coming in and something has to give. There's all this excitement going on here, the electron's getting very excited, and what's going to happen is it's going to be lost. And that's where this positive charge came from. So if we take a look at lithium, an example for lithium, we know that's an alkali metal. It's going to take 520 kilojoules per mole of energy. When that energy comes into my system, then I'm going to become an ion. So an atom becomes a positive ion, a cation. And this is where we started in the fall. So why does it want to do this? The reason that it wants to do this is it's going to become very stable, like the noble gases. So it does this to gain some stability. Now, it should make sense to you that once it gains that stability, it's losing this one electron. Now it's going to be like helium, electron configuration of helium. So then we have a second ionization energy. It's just called the energy needed to remove the second electron. Well, if we take a look at this, you can see that lithium is then going to become a +2 charge. That's not really what it wants to happen. So take a look at this difference in energies. I have 520 kilojoules per mole of energy, and remember a kilojoule is pretty small. To lose that first electron, then it jumps all the way up to 7,297 kilojoules of energy. That's huge, and the reason is because it's already very, very stable. It wants to hold on to the electrons that it already has. So in order to do that, you're going to have to apply a lot of leverage to get that electron out of there. And so that's just the difference between the first and second ionization energy. And if you didn't know where lithium was on the periodic chart, you could probably guess that that's where it is just because of the huge jump between the first and second energy, or ionization energy. So the ionization energies can be explained by electron configuration. I think that's the easiest way, or off-ball diagram, to take a look at this. If I have a more stable configuration, like the noble gases that I just mentioned, if I can get there to it, it's going to have low ionization energy. If it's a less stable configuration, the results in high energy. So if it's going to become less stable, that's what that means. So to become more stable, if it's easily can do it, it's not going to take very much energy to do that. So we saw this here with lithium. We already talked about this between its first and second ionization energy. Again, the last electron in is the first one to leave. So this would be the first ionization energy. And then, if I change my color here, one of the 1s electrons would be removed, and that would be my second ionization energy. And you can see that it's going to become less stable. So that's why we have this huge jump. Again, with magnesium, you can see the same thing, that the first ionization energy is relatively low, and that would be my 3s electron. And then the other 3s electron would take a little bit more energy. It wants to lose these because then here is my noble gas configuration. Every sublevel is full. I have 2, 4, and then 6 more. I have 10 electrons like neon. And in order to remove myself from that state, you can see that I'm going to have to add a whole lot of energy to lose that third electron. And when this happens, magnesium, remember, if you go look on your cation anion sheet, you're going to see this, because it really does want to lose these 2 electrons so that it becomes this noble gas configuration, as you see here. So the amount of energy here in the first and second ionizations is not that large. As you're going to see that metals want to lose electrons to become like noble gases. Okay, so we have just this general chart here for you. And ionization energy, generally, as I go across the period, is going to increase. And the reason that they do this is because it's going to increase because I'm reaching greater stability. And once I do that, it's going to be harder and harder to remove that electron. I have greater Zeph over here on this side of the periodic chart. and I also have smaller radii. Well, all of those things are going to play a part in that they really do not want to lose electrons. And you can see that as I get closer and closer, if you just follow along here, that they don't want to lose electrons, they want to gain. So if I'm right here with fluorine, it doesn't want to go this way, it wants to go towards neon. So ionization energy is going to be greater because it has greater stability, greater Z factor, smaller radii over here. It does not want to lose an electron. Now if I go on the other side and I'm going down my family, you can see that the ionization energy is going to decrease, meaning it's going to be easier to remove an electron. So it's going to be easier to take that away, it's going to take less energy, and the reason that we've kind of talked about is that it has greater radii, because I'm adding those energy levels, and it has less of a Z factor. Again, they're not holding it in, holding the protons, electrons in as tightly because I'm adding those energy levels. And so it's an increase in energy levels. And so all of these things make it much easier to remove an electron. And so this other chart that you can see right over here, it's a great pattern that shows you ionization energies. That here it is, it's really low at the beginning of a period, increases, increases, increases as I go up, because now in that noble gas configuration, I do not want to lose that electron. Drops again as I go to the other side of my periodic chart, as you can see with that sodium, and goes back up across the period. And this is continuous, and these are some of the things that Dmitry Mendeleev saw and studied in order to place them properly on the periodic chart. And you can see here some of these ambiguities that aren't nice and neat. Those is where we're hitting our transition metals. And they've always been a problem all year long, those little exceptions that we have. But in general, we can say the ionization energy is going to increase as I go across a period, meaning it's going to be harder to remove that electron. And as I go down, it's going to be easier to remove that electron. That's it. All right, I hope you have a wonderful night, and I will see you soon in class.